So here's another example. I want to. It's amazing how if your mindset is math and computer science, then you find I apply it to my whole life, right? How it can come up. All right. So here, my precondition is I'm born, right? Hopefully my parents were helpful. Right. My loop invariant is I'm alive and well and reasonably on track. Right. Don't expect too much of yourself. Are you alive? Are you well? Are you reasonably on track? Don't kill yourself, Right? One day at a time. Right? You don't need to solve all the world's problems today, though it's looking pretty daunting that we should do some of those soon. Right? Maintain the loop invariant. That's what your goal today is. Wake up. I had to go upstairs to my nephew and kick him a few times. Come on, dude, you're too depressed. I know you lost your job. Get out of bed. Right? Make a little progress. Your goal today is to make a little progress and to maintain the loop invariant. Make the world a little better and maintain the loop invariant. Right? Right? Everybody's good with this? That's religion. I just gave you how to live your life. Right? It doesn't get much better than this. All right. Everybody see we've done all these. And whenever you see this slide, it's an icon to say, we did everything for that algorithm, and now we're moving on to the next algorithm. All right? All right, so now we fill in some things that we're missing. All right? Where are they again? Did they go away? Here. Now we need to add in the proof that your program holds. Right? What are we going to add in? We're going to add in a measure of progress. We're going to add in that as long as you don't exit, you make progress every iteration. We're going to add that when you start, the amount of progress you need to do isn't infinite. We're going to add in that if your measure of progress gets down to 0 or something, then you would have exited by then, right? And here I'm assuming you'll note from the 79 to the 75 that a measure of progress is something that goes down, but I'm not religious about that. If you want your measure of progress to go up, more power to you, right?
As long as the exit condition is something that's up.
Yeah, exactly. Yes. Put the pieces in a reasonable direction, right? Yeah. In fact, in general in my life, if somebody wants to talk to me about aliens, I'm really good about it. I have no evidence about aliens, but I just want their conversation to be internally consistent, right? So it's same here. If you want your loop invariant to go, your measure of progress to go up, just be internally consistent. All right. All right. So I think these might have been my very first slides on this topic. So let's see how you like it. We're trying to get from home to school, right? What's my precondition? I'm at home. I know where home and school is. And postcondition is I've traveled it, right? What's an algorithm? Well, somehow it's got to get you between the two, right? And is this reasonable? Well, we don't really, before we run it, we don't even know where home and school are, right? We don't know what the input is, right? And we don't know the path, and there could be many, many paths. And what's also scary is that the computation may get really quite confused in the middle, right? You might end up in a tree, a bear might chase you. Who knows what might happen in the middle of this computation, right? And so if you remember about 2001, right, it's all about finite state automata. What state am I in, right? So here, where I'm standing is going to tell me everything that's true about my data structure, right? Where am I right now? Right? And so suppose I'm right there. What do you have to do with your code? You write code, you have to say, suppose I'm here, then what? Right? You have to say, well, what do I do next? Right? So where is it? Okay. Suppose I'm here. What do you need to do? Well, you'd like to say, if you're too enthusiastic, you're going to panic and drown. You might say, I need to get here. How do I get here? Right? That's going to kill you. Right? All you need to do is not even the best step towards school. I'm going to say you just got to take any step that gets you closer, right? Just don't worry about the entire computation, right? Just take one step. Right? Everybody got that? And what do we need with that step? Right? So wherever I am, you need to define what step I'm going to take. And what needs to be true about it? You need to get closer, right? According to some measure. And is that going to mean that I do this? No, it doesn't, right? Let's see. Or this is just saying, right? This is the circle which says, for wherever you are, you need to define how you're going to step, right? And this is the circle that says, whenever you step, you need to make progress, right? So if those together, is that going to prove that we're going to get to school? Right? Here are these circles which tell you how far you are from school, right? And what is this going to mean to us? There, right? It doesn't say that you're going to take a straight line, right? But hopefully it gets you there, right? And if you're panicking because you say, "Oh Lord, do I really know where we're going?" No, you won't know where you're really going, right? You're not going to know. And that's okay. Right? It's okay that you don't know. Some things, this is back to our religion, right? Some things we just will never know. Right? All right, so here we added some extra requirements, right? Right? So we have the requirement that when you start your measure, you're not too far away. And this measure says that, here I got a cross out. You know, if I took a step of distance 1 and then a half and then a quarter and then an eighth and a 16th, I'm always making progress, but you know you're not going to get there, right? So you got to make progress of at least 1, right? And this says, I may get home, I may get to school well before I get to measure progress 0. But I know if I get 0, I'm going to be there. I'm going to have exited. Right? So, what are we doing here? Okay, so, again, remember this whole thing is confusing, right? And you might get places that you don't know how to handle, right? You might end up in jail. You might end up a tree, right? That's a problem, right? And so that's why we're going to define these safe places, right? What does it mean to be in the safe places? It means you're not up a tree, you're not in jail, you're somewhere reasonable that we are willing to consider, right? And so then, and what is a safe place, right? This is going to be our loop invariant, obviously, right? Our invariance. It's a yes. I'm standing in a green place, or I'm not standing in a green place. And if I'm not in the green place, that means something's gone wrong and you better phone your lawyer, right? Something's wrong. And, but what do our steps have to say? We're going to assume that you're in a safe place. So you only have to define the code assuming that you're in a safe place. You don't have to worry about, in your code, you don't have to worry about getting out of jail. Right? So what's required of the step is you have to, if you're in a safe place, it does, assuming you're in a safe place, then it doesn't step to an unsafe place. Right? That's what A implies B means, remember? Doesn't say A is true. It says if A is true, then B is true. If you're in a safe place, you're going to head to a safe place. Right? And, right, so from this, an induction, right, does that give us that you're always in a safe place? Everybody's going to nod their head yes, but I'm tricking you because you've got to establish the loop invariant at the beginning. Right? Everybody good? All right. Right, establishing the loop invariant. All right, so here I think we're missing a slide. At some point we want to say, do we do everything? I don't know if we're there yet. All right, so Maybe it's later. Somewhere there's a step where we lay down all the things that we need to do and then prove that the algorithm works. And it feels like we're kind of in there, right? Right. The precondition says that you establish the loop invariant, right? Then do we have all the things we need? Well, if we prove you can establish the loop invariant and you prove you can maintain the loop invariant, then that by induction gives you that the loop invariant is always true. Right? What's our loop invariant going to be? S of I could be the statement after I iterations, the loop invariant will be true. Right? What are we doing here? We're saying after 0 iterations, when you first get there and you haven't iterated yet, it's true. What's this saying? It's saying no matter what happened in the past, if the loop invariant's true and you go around one more time, it's still true. Right? And then that gives us that it'll always be true. Right? Everybody good with that? Everybody following along?
The only thing I would say is for the previous one, you might want to say for less than I plus 1 on the...
Yeah. I often just struggle, but... sorry, for what? For... in?
At the bottom where you're saying for all I, like, it might be more helpful to show the process by saying for all I less than I plus 1, right? You know what I mean? Like, we're saying all of the previous ones are true, so that's true. So
yeah, sorry, I'm not actually even meaning to say that.
Yeah.
You're right, this is, I meant the brackets to be like this.
Okay.
So what I'm wanting to say is for every I, this goes to that.
Yeah.
So you're right. I should make notes of things to change, and we got 2 of them. Yeah.
The right hand expression that says AI, shouldn't that be I? Oh, never mind.
Like, because that's everywhere, but it's just that the early one already said that. So, like, as long as you have that universal quantification, then you're.
Yeah. So here, people see that. I want brackets here. I want to say for every I. If this is true, then this is true. Then they're all true. And I'm going to try to remember. I sometimes forget the changes I'm supposed to make. But, if anybody ever sends them to me, that's good too. All right. So then the exit condition, right? If we have the exit condition, this is saying that you eventually, this says that if you have sufficient progress, right, then the exit condition would be met. And when we exit, we know that the exit condition is true and the loop invariant is true, right? And then we get the post condition, right?